What's up everybody, and welcome to part 15 of my Basics of Deep Learning series. And in this video, we're going to code a neural net from scratch. So let's get right into it. So let's first make the import statements. So we're going to say import NumPy s and p, then import pandas as pd, then from sklearn model selection, we're going to import train test split function. And from sklearn learn.preprocessing, we're going to import the min-max scaler because we're going to min-max scale some of our features. Then to make some plots, we're going to import matplotlib.pyplot as pit. And then to make the plots a little bit more nicer looking, we're going to import seaborn as SNS. And then to make sure that the plots are actually depicted in the notebook, we're going to say matplotlib inline. So let's run this. And then we're going to say sns.set style. And here we choose the style dark grid. So now let's prepare our data. So we can say prepare data, and here let's first load in our data into a pandas data frame. So we're going to say pd.read csv, and the data is the Titanic data set, and let's print the first 5 rows of that. So this is what it looks like. And now first we're going to drop some of those columns because we don't need them in the moment. So we're going to say df.drop, and the columns that we want to drop are the passenger ID, then the name, then the ticket, and then the cabin. So let's run this, and then obviously we have to do that along the columns and not along the rows. So axis equals 1. Okay, so this one's what the data now looks like. And now to prepare it, let's look at df.info, and here we can see that we have 891 rows, and in the H column there are some missing values, as well as in the embarked column. So now we're gonna fill in those missing values. So missing values. So here, then we're gonna say df equals df.fillNA, and here we can simply pass in a dictionary where the key is the column name, and the value is then the value with which we want to replace the missing values. So in the case of the H column, we want to replace with the median H. So we're going to say df.h.median. So it's 28 in this case. So this is how we're going to replace the missing values for the H column. And then for the embarked column, we're going to replace it with the mode. So the value that appears most often. So we're going to say df.embarked.mode. And here to get the actual value, we have to index this. So it's going to be S. So this is our value with which we place the missing values. So now let's run this, and let's run df.info again. And as you can see, we have no more missing values. So now another thing that we're going to do to prepare the data is to one-hot encode some of our columns. So that, for example, the passenger class doesn't say 1, 2, 3, but then we have 3 columns for that. So passenger class 1, and then we have a 0, 1 indicating if that passenger was in class 1 or not. So here we're going to say df equals pd get dummies, and here we pass in our data frame and the columns for which we want to have a one-hot encoding. Those are the passenger class, the sex, the number of sibling and spouses, the number of parents and children, and then also embarked. So let's see what that looks like. So for example, this first passenger here was in class 3 and it's a male. And now one last thing that we want to do is to min-max scale some of our columns, which is going to be here the age column and the fair column. And that's because later on when we do then a matrix, a dot product, for example with this row here, then the dot product of that would be mostly influenced by those two values here, because they are so much higher than the values in the other columns. So that's why we're gonna min-max scale those two columns so that all the values are between 0 and 1. So we're gonna say df equals, first we're gonna create the scalar, so min-max scalar. So let's run this, that's created. And then the columns that we want to min-max scale are the age and the fair. And therefore then we're going to say this equals scalar fit transform those two columns here. So let's run this. Okay, it seems to be working. And now let's say df.describe to get some overview statistics. And here you can see the min values for the age and fair are now 0 and the max values are 1. So this has worked, and that's it for our preparation of the data. So now let's do the train test split. So therefore we're going to first create our input matrix and the label matrix. So we're going to say x equals df.drop, and you want to drop the survived column because that's the label, again along axis 1. And let's print this. And this now still is a data frame, so that's why we're going to here say values, so that we get a NumPy array. And then we create the label matrix. So here we're going to say then df survived and then values. So let's print this here. So this is what it looks like. And here I wrote those double brackets because if I just say, for example, survived and then values, then I get just this one-dimensional array. But I want to preserve here this matrix shape so that we have numbers of rows and a number of columns. So one column. So and now let's do the train test split. So we're going to say x train, x test, y train, y test equals train test split of x and y. And the test size is going to be 20%. And random state we're going to set to 0. So that we always get the same random split here. Okay, now let's create some helper functions. And the first one that we're going to need is our activation function, so the sigmoid function. So we're going to say sigmoid x, and this should simply return 1 divided by 1 plus np exponential minus x. So that's our helper function for now. And then let's set some parameters of the neural net. So first we're gonna set the learning rate again to 0.1. Then the number of epochs we're gonna set to 10,000. And then the n, which we're gonna need here because of our mean squared error. This is simply y train dot size, so the number of elements in our label matrix, which is then also going to correspond to the number of elements in our output matrix. So now let's determine how many nodes we're going to have in our neural net. So in the input layer, the number of nodes is going to be the number of columns that we have. So we can say xtrain dot shape to see how many columns. So 24. So that's how many nodes we're going to have in the input layer. Then the hidden layer, we're going to set the nodes to 4. And then in the output layer, we simply have 1 node because we simply want to see if the person survived or not. Okay, so that are our parameters. Oops. And now let's create our weight matrices. So this neural net here is going to be a tool, or just going to have 1 hidden layer. So we need 2 weight matrices. Therefore, let's say mp.random.seed, and here you choose 10. And then we're going to say weights 1 equals mp.random. And we're going to pick random values from the normal distribution. And here we set the standard deviation to 0.5. And the size is then simply an input. So the weights go from the input layer to the hidden layer. So times n hidden. And I also like to write out the dimension of this matrix. So this is going to be a 24 by 4 matrix. So now for the weights 2, we basically have to do the same thing. But here then obviously the number of rows is the number of hidden nodes, and then here number of columns is n output. So this is going to be a 4 by 1 matrix. Okay, so now let's create this. And now we can run our backpropagation algorithm. So we're going to say for epoch in range epochs. So first we're going to do the feedforward algorithm. So feedforward. And here in the previous videos, I always created the hidden layer inputs and then the hidden layer outputs. But actually we don't really need the hidden layer inputs in a variable, so we can immediately calculate the hidden layer outputs. So we're going to say hidden layer equals the input matrix multiplied with weight matrix 1. So mp.xtrain with weights 1. So with that calculation, we will move the neural net from here to here. And then to move through the nodes, we simply apply our sigmoid function to that. So I'm going to say sigmoid. And this matrix, now let's write down the dimensions of this matrix. So therefore we need to know the dimensions of our input matrix. So we multiply this matrix with that one. So the resulting dimensions will be 712 by 4. So then in the next step, we can do the same for the output layer. So we're going to say output layer equals sigmoid mp dot. Then here the hidden layers times weight matrix 2. Hidden layer weights 2. And this then, here we multiply then a 712 by 4 matrix with this one. So the result of that will be 712 by 1 matrix. So that's already the feed forward. Now let's do the backpropagation. And here basically the same thing applies. So in the previous videos, we first calculate the output error and then the delta, but this output error we actually don't need, so we can immediately go to the output delta. So I'm going to say output delta. And here what we have to do is to move from here to here in the neural net, in this first step, we have to take the derivative of our cost function here, which is then simply, so we bring down this 2 in front of here into this numerator, then this cancels out. So we have then 1 over n, and then simply our outputs minus the label. So, and this 1 over n we're going to do later on, as we've done in the previous videos. So here we simply then say output layer minus y train. So by doing that, we move from here to here in the neural net, and then to move backwards through the nodes, we have to multiply that with the derivative of the sigmoid function. And the derivative of the sigmoid function is simply the output of the sigmoid function times 1 minus the output of the sigmoid function. So here the output in this case is the output layer. So we simply multiply that then with the output layer times 1 minus the output layer. So that's output delta. So next we want to calculate the hidden delta. And therefore then we have to move from here to here. So we have to calculate the derivative of a matrix multiplication. And to move from here to here, then the opposite corresponding element of that, of the hidden layer outputs, is then obviously the weights. So we have to multiply somehow the output delta with weight matrix 2. So this is what we have to do here. So np dot output delta with weights 2. And if we look at the dimensions of these matrices, so the output delta, let's write that down. This is actually just the same as we had here, because here we're only doing element-wise operations and no matrix multiplication. So we want to multiply this matrix with that one. So that doesn't work because of the dimensions. So we have to take the transpose of our weight matrix 2 and then calculate this one with that. So here we simply take the transpose. And then by doing these calculations, then we have moved in the neural net from here to here. So then to move from here to here, we have to again multiply that with the derivative of the sigmoid function here. So this is then going to be the hidden layer times 1 minus the hidden layer. So let's also write down the dimensions. So output delta was this one, and we multiply that with the transpose of this. Is that correct? Output delta transpose of this. Okay, yeah. So that's also 712, and transpose is then 4. So that's the hidden delta. So that's back propagation. Now let's do our weight updates. Yeah, then we're going to say weights 2. And then to do the update, we simply subtract our learning rate times the derivative. So here we're going to then say minus equals learning rate times the derivative, so that we have to calculate. So to update the weights 2. So we're here at this point, and then we want to move to the weights. So the opposite corresponding element of that are these points here, so the hidden layer. So we have to multiply, let's write that down, np dot, the output delta and the hidden layer. So we want to multiply this matrix with that one. And the result of that obviously must have the same dimensions as our weight matrix 2, because otherwise we couldn't element-wise subtract it. So the result of this multiplication again must be a 4×1 matrix. So to do that, so we have to multiply this matrix with that one. So if we take the transpose of this matrix here, so hidden layer transpose, then we can multiply it with this matrix, so the output delta, and the result will be a 4x1 matrix. And then we also divide that by n, because that's this 1 over n here. And then for the weights 2, we basically do the same. Weights over 1 minus equals learning rate times, and now we are here on the neural net, so to say, and we want to move the weight, so we have to multiply the hidden layer delta with the inputs. So the hidden delta, this matrix, with this matrix here, and the result of that must have the same shape as the weights 1. So it must be a 24x4 matrix. So again, if we take the transpose of our x, so np.xtrain.transpose, and then multiply it with the hidden delta, then we get exactly those dimensions here. So hidden delta, and then we divide that also by n. So this should be it. And if you sometimes, let's pull up the neural net again, sometimes those dimensions here of the matrices might not be so convenient that we can simply look up how we should calculate them to see where we have to take the transpose or not. So if you would, for example, have here a 4x4 matrix, then we could multiply our output delta with the transpose of that, or we could just take the weights matrix as it is. So if that is the case, then to know where you should take the transpose or not, you then simply can think about what you actually want to calculate. So if you look at this hidden delta here again, so what we do here is we move from here to here. On the first step, we move from here to here. So again, then we have the opposite corresponding element of that is obviously the weights. So we want to multiply the output layer data with the weights. And what we then want to know is the piece of information that we want to get is that this value here, this should then tell us how a slight increase in this value affects the mean squared error. And since an increase in that value could affect or would affect the mean squared error over this path, and this path, we then obviously have to add those paths together. So we want to multiply the value of this node with this weight, plus the value of this node with that weight, plus the value of this node with this weight. So from the row of here, the output deltas, we want to calculate the dot product with the row of weight matrix 2, because those are weights 1, 1, 1, 2, and 1, 3, which is the first row of the weight matrix 2. So to do those calculations, so the first row of output data with the first row of the weight matrix, we simply then can take the transpose of this weight matrix and then calculate that matrix with that one, which is what we do here. And then here, to calculate this step for the weight matrix 2, the updates for the weight matrix 2, what we do here is we want now move from here to the weights. So obviously then we have to multiply that with the hidden layer data. And what we here want to know is how we should update, for example, this weight here. And since the opposite corresponding element of this value here, of this node, is this value, we have to multiply those together. And to know how we should update the weights, we obviously want to consider all of our examples. So what it leads to is that for the output data matrix, we want to consider all the examples, for example, for this node, so for the first column. So we want to consider all the values in the first column. and then we want to multiply that with all the values in the first column of the hidden layer data of the hidden layer. So we again want the dot product of this column and that column. So to do that, we can simply then take the transpose of this matrix here and multiply it with that one, which is what we do here. And if that didn't really make sense to you, you can, or I will put links into the video description to the places in the videos where I explained that in more detail. Okay, so now let's run this gradient descent step for one iteration. Weights 1 is not defined. Where is it not defined? Okay, I misspelled it. Weights 1. Okay, so now we have created the output layer. So if we've run through one iteration, and now to see how that, or to monitor the training process of the neural net, let's create some other helper functions that calculate the mean squared error and the accuracy. So here we're going to say mean squared error, and we put in the predictions and the labels. Oops, and then obviously the function should return the mean squared error. So now to understand how this function should work, let's create some predictions, and we're going to choose the first 5 rows of our output layer, and let's also print them. And then we do the same thing for our labels. So labels equals y train, the first 5 rows. Let's also print those. Labels. And now to calculate the mean squared error, we can use this function here. So we simply say predictions minus labels, and that we square. And of that, then we want to take the sum over all the elements. So we simply say sum, and this then we divide by 2 times n. And that's then our mean squared error. So this is how that function should work. And here then we have to determine the n, capital N. So we're going to say labels.size, and then MSE equals that calculation. So that's the mean squared error. Now let's create a function that calculates the accuracy. So here we're also going to put in the predictions and the labels. And the function should then return the accuracy. And the way we're going to do our predictions is that here we want to predict if a person survived or not. So we're simply gonna round those values here. So if the value is equal or bigger than 0.5, then we're gonna predict that the person survived, and otherwise we predict that the person didn't survive. So we can say predictions.round, and this array here we can now compare to the labels to see which of those predictions was correct. So we can say predictions.round equals our labels. In this case, all predictions were correct. So let's store this Boolean array in a variable called predictions correct. And then to calculate the accuracy, we simply calculate the mean of this array. In this case, we get a 1.0 because all the predictions were correct. It is then our accuracy. So this is how this function works. And now let's create a dictionary where we are going to put into our mean squared errors and accuracies over the course of the gradient descent algorithm. So we're going to say monitoring equals a dictionary where the first key is the mean squared error, and the value is simply a list to which we then append all the mean squared errors after each gradient step. And the second key is the accuracy, and here we also use an empty list. So let's create this, and then here in our for loop, let's create another comment, and here we're going to say monitor training process. I'm going to say mean squared error equals the mean squared error of our output layer and y train, and the accuracy equals accuracy of the output, and we put in the output layer and y train, and then we append those values to those lists here. So monitoring of the mean squared error dot append the mean squared error, and then basically the same thing for the accuracy. So accuracy dot append the accuracy. So that's that. And then here after the for loops, we're gonna transform this dictionary into a pandas data frame. So we're gonna say monitoring df equals pd.dataframe of our monitoring dictionary. So let's run this and let's see if that works. So do we have a data frame? And we do. And now let's plot how those metrics change over the course of the different gradient steps. So therefore, let's create some subplots. So we're going to say fig, axis equals plt.subplots. We're going to have one row and two columns, so they're going to be side by side. And then the figure size, I'm going to set to 15 and 5. So so we have those two plots, and now in this first plot we're gonna put the mean squared error. So monitoring df mean squared error dot plot. X is axis 0, and the title is the mean squared error. And the same thing we do for the accuracy. So let's just copy this. And then we're going to say accuracy. This is 1. And here the title is accuracy. So let's run this to see what happens. And as you can see, our learning curve looks like it should. So in the first, in the beginning, the drop off is pretty quickly, and then it slowly tapers off. Here the accuracy increases to somewhat above 80%. So I think we can stop training, so we don't need to train it anymore. So let's now see how it classifies new unknown flower that it hasn't seen before. So we're going to say test data, and here we can simply copy this feedforward calculation, but obviously then we put in our test data, and let's run this. And now let's also print the accuracy to see how good the neural net is at making those predictions. So here we put in the output layer and then the labels from our test set. So now let's see what that is, and we get an accuracy of 81%. So I think it should be clear that the neural net has learned that, or how to distinguish or how to predict if a person survived or not. Because this, for this data set, it's a relatively decent accuracy. So with that now, we have basically answered those two questions here, which we posed in the first video of the series, namely how does the algorithm make a decision and how do you determine the right parameters. And with that now, I will end this series. So thanks for watching, and hopefully I will see you in one of my next series.